Good evening, my dear friends. Today we will discuss about the Raoult's law, all full discussion, and thereafter which one novice at any constant temperature or concentration. Raoult's law, that is called ideal solution, and what do you mean by non-ideal solution? And after that, what is the behavior of to make a ideality? And after that, positive and negative deviation. And at the end of this topic, we will discuss that we can take a Raoult's law as a special case of Henry's law. All discussion to be done in this video. So please try to watch this from the start to the end. Right. So let's start. Today we will discuss the Raoult's law. Basically, Raoult's law is a scientist, French chemist F. Raoult. He studied the pressure of a binary solution of a volatile liquid, that is for, you can say, benzene and toluene at a constant temperature, and from a general theory that is known as the Raoult's law. So you can see here the law is written, that is the partial pressure of any volatile component of a solution at any temperature is equal to the vapor pressure of the pure component multiplied by the mole fraction of that component in the solution. So what is happening here? So it is the any temperature that is equals to the vapor pressure of the pure component multiplied by the mole fraction of that component in the solution, right? So now that we have to give some representation, that is this is the theoretical expression, and we have to give the some mathematical or something like that. So see that here you can say that A and B, if two are the two immiscible liquid, right? So, and Na and Nb is the number of moles of A and B, and you can say that Xa and Xb, that is the mole fraction of A and B, and P and Pb. If you this Pa and Pb, that is, if you make a solution upon mixing this A and B, then the partial pressure of A is known as Pa, and partial pressure of B is known as Pb, and this P naught A and P naught B indicate that if it is in standard condition, that means it is a pure A, then this is P naught A, and if it is pure B, then this is the P naught B. So according to the Raoult's law, we have Pa equals to Xa P naught A and Pb equals to Xb P naught B, because we have the Raoult's law, that is the partial pressure, of any volatile component of a solution that is given. So that's why this is Pa, and for pure component this is P naught A, right? So at a component temperature of a solution at any temperature is equals to the vapor pressure of the pure component multiplied by the mole fraction of the component in the solution, right? So this is for, so if it is B, for case of B, then this is Pb equals to Xb into P naught B, right? So this is the thing. Now see that if your vapor, that is what you have, that vapor, that is basically, if it is like say ideal gas, if your vapor likes an ideal gas, know that in a normal temperature and pressure, your all the gas is real gas, they are not the ideal gas. So special condition and temperature is required to make a real gas in an ideal gas. So in that case, what do we have to do? If vapor behaves like an ideal gas, then you know that according to Dalton's law of partial pressure, this is in class 11, I think it is in gas liquid, that states after. So Dalton's law of partial pressure, that is total vapor pressure, equals to, so this will be capital P, that is equals to P and Pb, because if A and B mix and make a solution, then the partial pressure of A and partial pressure of B, that will create the total pressure. So if you put that value PA, because we know from Raoult's law that it's XA P naught A and PB equals to XB P naught B, right? So then capital P, that will be equals to XA P naught A plus XB P naught B, right? So this is, you can write in the ith condition, that is Pi, that is the equals to Xi P naught I, because if you have I component, that is the partial pressure of the ith component that is in the solution, that is equals to the mole fraction of the ith component multiplied by the pressure of the pressure in its pure ith component, right? So this is the vapor pressure and that representation, right? Now see that there is some diagrammatically representation, right? So see that here, if you see this P and PB, this is a there is some question that why this value is higher but this value is lower, because we have taken A naught and A and B, both are volatile liquid, right? But we have taken that volatility of A is greater than that of the B, because if it is more volatile, then it will be more in the vapor phase, so that will create a more vapor pressure. So that's why that point is here, right? Now see that when X is equals to 1, so with increasing X, so you are so if X is going to mole fraction is going to left to right, then you can say that mole fraction of A, that is decreasing, whether mole fraction of B is increasing. So when X equals to 1, that is basically you have only pure solvent or you can say pure substance A, so that's why this is known as P naught A. So that pressure created by that substance, that will be P naught A. But here see that XB equals to 1, so that's why this is P naught B, right? So this is the diagrammatic, because you can say that XA is here increasing, so that line indicate that PA, and here see that XB in this case increasing in this way, the left to right, so that's why this line indicates this, and this if we join this line, then we get the total pressure, that is basically nothing but partial pressure of A plus partial pressure of B, right? So this is the vapor pressure of ideal solution. Okay, so this is the vapor pressure of ideal solution. Okay, now there is some topic, that is what do you mean by this ideal solution and non-ideal solution, right? So what do you mean by this ideal solution and non-ideal solution? See carefully, there is some example of this. First one, you can relate that these two are ideal and these two are non-ideal. So you cannot say by seeing this mixture, because you have to study well to say about this ideal condition and non-ideal condition. So that is basically liquid pairs having similar character forms ideal solution, right? So that implies that intermolecular force or cohesive forces in this solution are completely uniform. Try to understand that intermolecular force or cohesive force, there is another force also, adhesive force. So here what is happening, that intermolecular force or cohesive forces in this solution are completely uniform. So you can say that here we are using liquid A and liquid B, right? So in the magnitude of these forces between molecules AA and BB and A and B are of same magnitude, so that they can form the ideal solution. So the example of this ideal solution is, this is benzene, this is C6H6 benzene and C6H5CH3, that is basically toluene. One hydrogen is replaced by one CH3 group, this is toluene. So benzene toluene, and this is CCl4 carbon tetrachloride and SiCl4, that is silicon tetrachloride, right? They both are example of this ideal solution. But you can say that so this is the ideal solution, and they obeys this Raoult's law at any constant, any temperature and concentration scale. So they obey the Raoult's law, right? But in case of non-ideal solution, this is for non-ideal solution. This pair can make a non-ideal solution, that is basically acetone, keto group, and this is aniline, amine group, and ethanol and H2O. These two pairs, this pair can make a non-ideal solution, and this pair can make non-ideal solution. Now, what is the difference between this ideal solution and non-ideal solution, right? For that, that first one is it obeys Raoult's law in all temperature and concentration, right? But in case of non-ideal solution, they doesn't obey the Raoult's law at any constant temperature or concentration, right? Now, there is one thing in your book you can see that del V mixing is 0 in case of ideal solution, and del H mixing is 0 in case of ideal solution. So this is the criteria for making an ideal solution. But the thing is that what do you mean by this del V mixing and del H mixing? That in case of ideal solution, due to having similarities of shape and size of ions, there is no change in intermolecular distance, right? So if there is no change in intermolecular distance, then what happens? So there will be del V mixing, that will be 0. But in case of non-ideal solution, there is no such cases, because of why del V mixing not equals to 0. So what is happening? Due to having similarities of shape and size of ions, we have seen that liquid pairs having the similar character forms the ideal solution. So here also, as their similar character forms the ideal solution, so the criteria that having the similarities of shape and size of ions, so there is no change in the intermolecular distance. So del V mixing is 0. So you can say that 20 ml benzene and 1 ml benzene, so that will make 20 ml benzene and 10 ml toluene, that will make the 30 ml solution. But in case of non-ideal solution, if you add say 20 ml and 10 ml, that will not make this 30 ml, maybe less than, maybe greater than that. We have to discuss about this, but you have to mention that del V mixing for this case ideal solution is 0 because of similarities of shape and size. So there del V mixing is 0, intermolecular distance is 0, intermolecular distance remains same, so that's why del V mixing is 0. Okay, but here in case of there is no such cases. And another thing, that is del H mixing is 0. Why del H mixing is 0? Because intermolecular force or cohesive forces in this solution are completely uniform. So that's why this is a athalamic. So you have known that del H is greater than 0, then this is the endothermic, and if it is del H is less than 0, so this is the exothermic. But you have to have at least one idea about that. Del H mixing equals to 0, that means this is a athalamic process. But in case of non-ideal solution, this is not a athalamic process. Okay, thank you. So this is our topic, and the next topic we will discuss about the vapor pressure of the non-ideal solution. Okay, thank you. So if you like this video, then please subscribe our channel and stay with us. Okay.